Today, I'll tell you about a project where we used some special properties of harmonic functions to design an algorithm for ray tracing a new class of surfaces. Formally, a function is called harmonic if the sum of its second derivatives is equal to 0, but the details don't matter too much for us today. You should just know that harmonic functions are a special kind of function which are very well understood mathematically. And when people introduce harmonic functions, they often show an example like this, a nice smooth function with a characteristic saddle shape. But these pictures are actually kind of deceptive, because many of the harmonic functions that really show up in practice are actually a lot nastier, with various kinds of singularities where the function's value can blow up to infinity. And we'll see in a few minutes how these singularities can cause all sorts of problems when we try to do computations with these harmonic functions. The particular computation that I'm interested in today is intersecting a ray with a level set of our function. So we start with a harmonic function f and a ray at some point in space, and we pick out a target level set, say the set of all points where f equals 0, and then what we want to do is to find the time when our ray first intersects our level set. Once we can calculate these ray surface intersections, we can then in turn easily render level sets of harmonic functions directly. And while this may sound kind of specific, it turns out that level sets of harmonic functions show up everywhere. To name a few examples, they show up in reconstruction algorithms like Poisson surface reconstruction or mesh repair with generalized winding numbers. They show up as shell structures in architectural geometry and space-filling surfaces in digital fabrication. They can be used as spanning surfaces for nonplanar polygons and curve networks, and they also show up all over the place in math and physics, for instance as Riemann surfaces or hyperspherical harmonics. But despite their ubiquity, level sets of harmonic functions are hard to render with existing techniques. One problem is the fact that they may have these singularities. This comes up, for example, in the implicit function used for surface reconstruction. If you try to find ray surface intersections with something simple, like ray marching with a fixed step size, you can easily tunnel through the surface, leaving gaps. And if you try to run a more sophisticated algorithm, like sphere tracing using some purported Lipschitz constant, you get a smoother surface away from those singularities, but you still leave behind big holes in the surface. For those of you familiar with sphere tracing, this is because no valid Lipschitz constant exists around the singularities, so the method's guarantees don't apply. And of course you can try to fix this by decreasing your step size in ray marching, or increasing your purported Lipschitz constant in sphere tracing, and this makes things a little better, but really doesn't fix our problem. Another big challenge is that level sets of certain singular harmonic functions may have boundaries. And if you try to intersect rays with these surfaces, using standard root finding techniques like Newton's method, or interval analysis, or bisection search, or even just try to run standard mesh extraction methods like marching cubes, you get all sorts of junk, even for very simple surfaces. To get a better look at what goes wrong with these existing methods, and how we can fix things, let's take a closer look at sphere tracing. In its simplest form, sphere tracing is an algorithm to compute intersections with level sets of signed distance functions. Here, I've drawn the signed distance function for a curve in the plane. At any point, the value of our signed distance function gives the distance to the curve. Now, if we have a ray, and we want to compute its intersection with our curve, sphere tracing says that we should first evaluate the signed distance function at our starting point, which tells us the distance to the curve. In particular, if we draw a sphere of that radius, the curve can never come inside the sphere. So we can step along our ray direction to the boundary of the sphere and be sure that we never accidentally cross the curve. We'll call this a safe step. Now we have a new point, we can evaluate our signed distance function again, giving us another empty sphere, so we can take another safe step, and we can keep doing this until our signed distance function tells us that we've gotten close enough to the curve, at which point we return an intersection. And it turns out that it's easy to generalize sphere tracing beyond these signed distance functions to a broader family called Lipschitz functions. You can think of these as functions whose gradient is always smaller than some constant L called the Lipschitz constant. And the important fact about Lipschitz functions is that the difference in value between 2 points can never be more than L times the different distance in space between those points. So knowing the value of a function at a point provides a conservative bound on the distance to any other level set. In turn, this lets us run sphere tracing on these functions. And people have designed Lipschitz functions to encode some incredible scenes, like this iconic sphere-traced snail designed by Enrico Chiles. But the problem for us is that many harmonic functions that people really care about are simply not Lipschitz. One illustrative example to think about is the angle function, often called atan2 when you're programming, which takes in a point and measures this point's angle with the positive x-axis. If we plot the angle function, it looks something like this. But now consider these 2 points, whose angles differ by pi over 4. we can move them closer and closer to the origin without changing either of their angle values. No matter how close these points get, the function values never get any closer. And in particular, we cannot use these function values to get a distance bound for sphere tracing. The main idea of our algorithm is to get distance bounds from something known as Harnack's inequality for harmonic functions. If you have a positive harmonic function f on a ball centered at a point x, then for any other point inside this ball, Harnack's inequality gives us bounds on the value that our function can take. And the particular form is really not important here. I just want you to see that we have these lower and upper bounds, depending on the radius big R of the ball, and the distance little r between our 2 points. And if you do a little bit of algebra, these bounds actually tell you that it's always safe to take a step of the following size if you're starting from the center point x. Even though our function is not Lipschitz, we can use the fact that f is harmonic to obtain a distance bound. Now there's just one little detail left. I said at the beginning that your function has to be positive, but what if f is not always positive? Well, it's easy enough to add a constant to your function to make it positive over this ball. So in order to find these safe step sizes, all you need is a valid ball radius and lower bound on your function. And once we have these safe steps, our resulting Harnack tracing algorithm is pretty similar to sphere tracing. Starting from a point x0 and walking in a direction d, we start by picking a ball radius on which f is non-singular, shift f to be positive on that ball, and calculate a safe step size using the formula from the last slide. Then we take a safe step in the ray direction, and now we just repeat until our function value gets close enough to the target level set value. I won't have time to go into the details of how you can derive these radius and shift values, but it turns out to be pretty similar to computing Lipschitz bounds for sphere tracing, and if you're curious, we work through many examples in the paper. Anyway, since our Harnack tracing algorithm is so simple to implement, we were able to test it out in a lot of different places. We incorporated it into the PBRT ray tracer, wrote WebGL shaders on ShaderToy, and even incorporated our method into Blender's ray tracer to obtain both real-time previews in Blender's editor, as well as more polished renders with richer features like shadows and reflections. Now let's take a closer look at some of the applications that I briefly mentioned earlier. One example, closely related to the angle function that we were talking about, is the generalized winding number, also known as signed solid angle. Jacobson et al. Observed that you can take in an input mesh with holes and fill in those holes with a smooth surface, given as a level set of the signed solid angle function. Here we use Harnack tracing to directly render this level set, reproducing an example shown by Jacobson et al. Without having to explicitly mesh the surface. The signed solid angle function actually defines surfaces filling in any loop in space, allowing us to visualize spanning surfaces for nonplanar polygons. Solid angle also shows up in architectural geometry, where it's used to design architectural grid shells. And again, we can directly visualize these surfaces via ray tracing, bypassing the mesh-based optimization previously needed to construct these grid shells. We can also directly ray trace interpolating surfaces for point clouds, effectively visualizing the results of the classic Poisson surface reconstruction algorithm without requiring any volumetric meshing or linear solves. As a more abstract example, we can use Harnack tracing to visualize Riemann surfaces. These surfaces play a key role in the study of complex analysis, but much of their interesting behavior happens around singular points, which are hard to resolve with standard techniques. We can accurately render them with Harnack tracing, and we can seamlessly combine them with standard sphere tracing to illustrate the classic observation that Riemann surfaces look a lot like the spirals in parking lots. And one final example comes from digital fabrication. The gyroid is a triply periodic surface, which is often used for filling space inside of mechanical designs. Interestingly, the implicit representation of the gyroid is not a harmonic function in 3D, but we show that it can be seen as a slice of a harmonic function in 4 dimensions, allowing us to find safe step sizes and render the surface anyway. In the paper, we talk more about how our method can be extended to large families of other non-harmonic functions as well. Thanks for listening.